Welcome to Ask and Learn.
Here we'll see that the force of gravity, you can reckon with it in many the same ways that you reckon with the electrical force. So we're going to call E the gravitational field, and I have shown one gravitational field vector there. But actually the vector fills all space, but this will help us visualize some other things. So imagine all of space filled with vectors that are all pointing in the same direction with the same length. So we're going to take a 2 kilogram mass and we're going to ask, what is the gravitational force on it? Now, if this were a charge in an electric field, we would just multiply the electric field by the charge to get the force. So we're going to do a very similar thing. We'll take the mass and we'll multiply it by the gravitational field. By the way, I usually like to use G vector for gravitational field, but here I think they're trying to show the similarity with the electric field. Okay, so we have 2 times 5, or 10 newtons in the x direction. And let's go ahead and use the IJ notation. Recall that those just mean a direction in the x or y. They have magnitude of 1, but just point in a particular direction. And then we have 2 times 12, which is 24 newtons, and that goes in the y direction. Okay, so if we can do the usual things with the force of gravity, it will point in the same direction as the E vector, and we can find its magnitude in the usual way with Pythagorean theorem. So 26 newtons in this case. Now, we can start to even draw an analogy with potential. Of course, this will not be in units of volts, but in electricity, a potential is at a point relative to a reference point. And here we'll refer to the origin as a potential of 0. And that is minus the line integral of the, in the case of electricity, the electric field, times the path, called a line integral, from the reference to point A. Okay, so here we're going to just find that potential for 2 points and see if it makes some sense. So let's take point A is 12 meters and origin in the y. And so that is the y direction is not moving anywhere. So that would be EX times DX between 0 and 12. And of course, the EX is just a positive number, 5. So we have dx from 0 to 12. And we'll worry about the units in a little bit, but it's going to be newtons times meters over kilograms. Yeah. Okay, so that is minus 60. And instead of saying newtons times meters over kilograms, we'll say joules per kilogram. A joule, reminder, is a newtons times a meter. And if we can go think about what we're doing to that particle, we're basically moving it in the x direction. And that is in a partial direction that goes with the gravitational field. And so that's kind of like dropping something in Earth's gravity. Yes, the potential will lower. And point B, let's try one more point because these are going to come into play later. So point B is 5 meters. So VB, yeah, this was VA. And point B is 0.5 meters. And so the x direction is not changing, but just the y. So we would just multiply, let me see, it's 12. Well, let's go ahead and write it out. EY dy between 0 and 5 is minus 12 dy 0 to 5. And that is minus 60 joules per kilogram. Okay, so the useful thing about potential in electricity is it is related to the potential energy of moving a particle around in the field. And we can define potential energy in a similar way here. We can say delta U is equal to, instead of charge times delta potential, in this case, it's mass times delta potential. And let's see, the first potential energy difference that we want to find is between 12 meters, between 0, 0 and 12 meters, 5 meters. That doesn't look right. Okay, origin. Okay, there's always a point, but we don't want to make it look like the potential energy is a vector. But U initial is m times the potential at 0, which is our reference point. U final is at point 12 meters and 5 meters. And we can think about this in 2 steps. So we can think about the potential difference between 0 and 12 meters, which we found in the x direction, which we found to be minus 60 joules per kilogram. And then between 0 and 5 meters is another minus 60 joules per kilogram. And that is minus 240 joules. Okay, so initial was 0. So that's one case. And see how we use the values we found for the potential difference, which is what you could do in electricity as well. And now we want to go from 12 meters, 0 to 0.5 meters. We can certainly use the same sorts of logic. Okay, at 12 meters, 0, the potential energy initial is minus 60 joules per kilogram times the mass. And then we're going to move it to 0, 5 meters. And again, the U final is minus 60 joules per kilogram times mass. And so delta U is, it wipes itself out. Okay. So kind of a useful thing to see that you can treat gravity very similar to electricity. I suppose what's kind of difficult to do, though, is to create a uniform gravitational field. Uh, I mean, naturally, one happens near the surface of the Earth, but it isn't slanted like the example here.